Okay. Okay. So this is the microwave range, approximate range. Yes. Actually, currently we use fiber. Okay, in Sri Lanka, most operators used fibers as their backbone mobile operators. Okay, most mobile operators use fibers as their backbone network. And SLT is not only a mobile operator. Okay, it is also a fixed line operator. SLT Mobitel. Uh, these are, I hope, totally use fiber networks. Okay, as their backbone networks. Okay. Cost effective, Chandimal, I don't have a good idea about the cost effective. Okay. I think microwave links are more cost effective because you know that if we need to set up a microwave link between two city, between two points, okay, what you have to do is, so normally for the microwave links, no dedicated tower constructed, okay. So normally towers are there, no mobile towers are there to locate those phone antenna. Those are called set antenna. Okay. So these towers are used for the microwave link also. Okay. So here what you have to do is you have to uh, put the microwave dish here. Then there is uh, another equipment called ODU. Okay. Then you can directly connect it to another unit IDU. That actually IDU, this ODU is a converter, frequency converter. Okay, it convert IF into microwave. This IDU is the modulator and multiplexer. In my internet connection, yes, okay, I think it is okay. Now I connected to my phone, okay, so I think it will be okay. Okay, so I will draw it clearly, okay. So if you have a tower there, what you have to do is you have to locate the microwave dish, not portable antennas, okay. This is a dish antenna. මේක අර බෙරයක් වගේ තියෙන්නේ. ඔයා දැකලා තියෙනවද? දැන් මොකද මේ කැම්පස් එකේම තියෙන ටවර් එකේ. මේවා dish antenna. අර සැටලයිට් වලට යූස් කරන antenna, parabolic antenna. parabolic හරි ඔයාට dish antenna කියලා කියන්නේ. මොකද dish එක වගේ. මේවා තියෙන ලොකු antenna තියෙනවා. These are very big antenna. Okay. So maybe around 6 meter diameter antenna are there. Okay. So these are very huge antenna. Okay. 3 meter diameter like this. Okay. So there are small antenna also there. As I can remember, 1 meter diameter, 0.5 meter dish. Okay. So those kind of, there are many type of, that is depend on the distance. Okay. So if we have to use, if two links has big distance, huge distance, we have to use a higher diameter antenna. Otherwise, we can use small diameter antenna, small antenna. Okay. So what we have to do is we have to connect the antenna here. Then antenna is connected to the ODU, that is a frequency conversion, and amplifiers are also there. Okay. Then this IDU, ODU is connected to what is called IDU, indoor unit. That is actually the multiplexer and demultiplexer. This is multiplexer and demultiplexer. And also the modulator part also doing there. Okay. It also function as a modulator and demodulator. Okay. So only this setup. So other side also you have this setup. Okay. Then what you have to do is you have to make this two antenna line of sight. Okay. Line of sight. We called it antenna line. Then this link will be okay. But if you are going to use fiber cable between these two location, what you have to do is you have to lay a fiber cable from here to here. So that will be very costly because this will be go through other lands, maybe going through the roads. Okay, so we have to get the approval from RDA and other government authorities. Okay, um, so I think this and it is also will get very time consuming. Okay, so I think it is easy to use this wireless link. Okay, rather than this wired or optical link. Okay, so I think more cost effective one is this one, the microwave link. I'm not sure. Okay, but there are many advantage over optical fiber over links. Okay, uh, there are many advantage of optical fiber over this microwave links, especially high data rate, low latency, then no the noise not affected. Okay, so there are many advantages. So that they are using fiber. Actually, these microwave links may be not may microwave link speed may be not enough for 4G and definitely for 5G. Okay, at least for 4G also these microwave links are not used. Normally use optical fiber. We are using gigabit bit Ethernet through this optical fiber. Okay, for the 4G network backbone. Okay, so previously all of almost all the actually all mobile operators in Sri Lanka used, okay, mostly widely used this microwave link. Okay, microwave link for the terrestrial communication. That means local communication. Okay, uh, uh, as a backhaul network. Okay, that means as I told you, there are many towers. Okay, and our phone is connected to that tower. There is equipment, transceiver. Okay, transceiver unit in the tower. So this transceiver unit should be connected to the uh, switching room or core room. Okay, or network. Okay, so this connection is done by microwave link previously. Okay, so it is a microwave network, backhaul network. Okay, so maybe if you have another tower, okay, maybe this tower should be connected to here. Then all these two information you can send this to the core network. Okay, so likewise, there are many towers. Okay, and only one core networks are there. So these all towers are connected to this one, mostly using microwave link. Okay, mostly using microwave link. But now these microwave links are replaced by fiber, uh, especially to achieve a high data rate. Okay, otherwise it is not enough for 4G. Okay, so these microwave links are now actually um, these microwave links are now actually replaced by fiber. Okay, so most of the students think that microwave is not an important subject because they are focusing on this point on. Okay, actually this is very active area previously. Okay, because there are dedicated engineers works for this microwave links. Okay, they are called transmission engineers. Okay, now that post is there. Okay, transmission engineers are there, but now they are dealing with most probably uh, Ethernet network, gigabit Ethernet network through fiber. Okay, not microwave links. Okay, so this part is only actually now replaced by fiber, but these are we can't replace. Okay, by fiber. Okay, so for this application, we need to have microwave communication. Okay. Otherwise, we can't achieve this through wired communication. Okay. So these are very active field in engineering world. Okay. In communication engineering world. Okay. So microwave engineering is very important. Okay. That subject is very important. And also, as I told you that when we are designing these circuits, okay, satellite circuit, radar, mobile communication, Wi-Fi, okay. So for that one, we have to develop filters, oscillators, okay, circuit components, okay, oscillators, amplifier, okay. So when we are designing these components, these are basic components, okay, and antenna, okay. So we have to directly deal with microwave engineering, microwave principles, okay. Otherwise, we can't achieve these circuits, okay. So this subject is very important. Don't forget it, okay. Okay. Then uh, we have uh, started our discussion from transmission line, okay. Transmission line, okay. Transmission line means the medium, okay. The medium we use to communicate, okay, that is the transmission line. Uh, this may be not the definition, okay, it is just explanation, okay. Uh, that is actually the medium, okay. So as you know, there are two type of transmission line, okay, guided and non-guided. Maybe you can remember non-guided, okay. And we have focused on guided uh, transmission line, okay, transmission line, okay. So guided transmission lines are, there are many type of transmission line, copper transmission line, okay, copper TX line, okay, used for microwave communication, okay. So for example, maybe you know that coaxial cable, twisted pair, then microstrip line. These are very popular copper transmission line, copper media to transmit the signal. Okay. And also we have to learn about waveguide also. Okay. Waveguide, that is another type of transmission line. Okay. And of course, optical fibers are also a transmission line, but we are not use it for microwave communication. Okay. Especially we are using this copper transmission line and waveguide for microwave communication. Okay. So we will learn these two transmission line later. Okay. Uh, Actually, we have already started this discussion. Copper transmission line, copper transmission line. Okay. Copper transmission line. Okay. Okay. So I will come to the our reference book. Okay. Mm, no, microwave non-guided means we are using just microwave radiation. Okay. Non-guidance means we are using radiation. Okay. So we are using radiation. Okay. So microwave are unguided also. Unguided because for the satellite communication, radar, okay, Wi-Fi, okay, these are unguided. We are using radiation, no, microwave radiation. So it is an unguided one. Okay. But now we are talking about guided transmission line. Okay, because in circuits we have mostly guided transmission. Okay, in microwave circuits, okay, actually we are mainly focused on microwave circuit. Okay, microwave circuit. Mostly we are focusing on this subject. Okay, so we have to analyze and design circuit. Okay, we have to analyze and design. That is our main task actually. Okay, so as I told you, this microwave analyzing can be done using uh, transmission line theory, or using Maxwell equation. Okay, Maxwell equation. Transmission line theory also derived using Maxwell equation actually. Okay, but we can directly use this one. Okay, now actually we are learning about transmission line theory because our focus on microwave circuit analysis. Okay, we are not focusing on these things. Okay, I just tell you the application. But if you are interested, we will discuss these things also later. I have uh, I have uh, normally fair idea about mobile communication and also a small idea about this satellite communication and little idea about radar. Okay, so if we need, we can discuss these things also. Okay, I have engaged with this microwave link actually. I think I have engaged with microwave links around 5 years. Okay, so I have a good idea about this microwave links, planning, implementation, all things. Okay, optimization. Okay, so if we need, we can talk. Okay, but uh, in our subject, okay, in our module outline, we are mainly focusing on microwave circuit analysis. Okay, so that is why in circuits we are using guided media for the transmission. Okay, as I told you that. Okay, so you know that if you consider our, for example, if you consider our phone. Okay, so basically our phone has antenna. Okay, actually there are 4 patch antenna normally used. Okay, so these antenna are connected to a so if you consider the receiving part. Okay, this is connected to a filter. Okay, then it is connected to a amplifier, low noise amplifier, maybe low noise amplifier may be here. Okay, low noise amplifier, then demodulator. Okay, then we have to decode the signal. Okay, decode the signal. Then we have to use analog to digital conversion. Then that signal is sent to the microphone. Sorry, yeah, microphone. Okay, so this kind of path is there. Okay, so there are many component we use: amplifier, filter. Okay, and this demodulator. For the demodulator, definitely you have to use oscillators. Okay, and here we have to use the analog to digital conversion, ADC, DAC. Okay, so there are many type of, yeah, sorry, I'm sorry, it is connected to this speaker. Okay, this is a speaker, not the microphone. Sorry. Yes, very good. Okay, thank you. Okay, so it is a speaker actually. Okay, so there are many components. Okay, so we have connect these component. Okay, so that connection is also doing by a copper strip, copper medium, or sometimes we are using waveguide also. Okay, we are using waveguide. For example, sometime antenna to maybe amplifier, we are using sometime waveguide. Okay, but inside the phone, okay, we are using copper. Most probably copper strip. Actually, micro strip we are using. Okay, so these are also transmission line. Okay, so to analyze this circuit, this transmission line part is very important. Okay, so that is why we are first focusing on this transmission line. Okay, so we have talked something, okay? Uh, so here the copper transmission line is model. It is modeled as a lumped element circuit. Lumped element means inductor, capacitor, and resistor, okay? So actually, if you consider transmission line, okay, I will explain this very little, okay? If you consider transmission line, for example, this is a transmission line, okay? And here we have connected plus and minus. This is the line, okay? And this is the ground, okay? This is a ground, okay? So all the transmission line has this copper transmission line has this structure. For example, if you consider coaxial cable, we have an inner conductor, okay? Then we have uh, dielectric media. Then we have outer conductor, okay? This inner conductor is working as a line plus, and this outer conductor is acting as a ground, okay? So here two um, terminals are there normally, plus and minus. This is the line, and this is regarded as the uh, yeah in coaxial cable. Actually, the outer conductor is a mesh, okay? It is a mesh. uh, so we have inner conductor. It is just normal cable, copper cable. Then we have a dielectric media, okay, like this, okay? And around this we have a copper mesh actually for a coaxial cable, okay? So same structure is mentioned here, okay? So you can see that here you have plus, that means the inner conductor maybe, and this may be the outer conductor, if you consider this as a coaxial cable, okay? And also this can be a microstrip, okay? The same things are valid for microstrip also, okay? I think you have seen microstrip. Uh, Give me a moment, okay? Hello. නෑ මම බැලුවේ මංගාවර මයික්‍රෝ ස්ට්‍රිප් ඇන්ටනාවක් එහෙම තිබ්බම ඇන්ටනාව නම් තියෙනවා හරි. Because we have to learn about the micro strip also. I will show it to you maybe. So can you see this? Can you see this? Okay. Okay. So actually this is a patch antenna. Okay. This is a patch antenna. This part is the antenna. Okay. So this antenna is constructed on this. This is we call the substrate. Okay. This substrate are used for microstrip. Okay. And you can see that there is a line. This is the transmission line, feeding point. Okay. This is the feeding line. This is the feeding line to the antenna. Okay. So you know that for example, in our home TV, we use coaxial cable to connect our TV with the antenna. Okay. Here, so you can see that here we are not using coaxial. Okay. We are using this kind of copper strip. Okay. This is called microstrip. Okay. So here we have the ground plane. This is the ground, and this is the line part. Okay. This is the line part. No, this is antenna. මේක ඇන්ටනාවක් කොල්ලෝ SIM card එක කියන්නේ ඒකේ සර්කිට් යන්නේ. එතකොට එයාගේ අර data හැම තියෙනවනේ මේවා කළා. මේක ඇන්ටනාවක්. ඒ කියන්නේ මෙතනින් අපිට මේක පැච් ඇන්ටනාවක්. දැන් අපේ ෆෝන් එකේ සිග්නල් එක අපිට රිසීව් වෙන්න මේ වගේ ඇන්ටනාවකට පැච් ඇන්ටනා. මේ වගේ හතරක් තියෙන මීට වල පොඩි. හරි. මේක මේ 1 GHz වලට වගේ හදලා තියෙන එකක්. හරි. එතකොට මේ වගේ පැච් ඇන්ටනා තමයි අපේ ෆෝන් එකේ තියෙන්නේ. මේක ඇන්ටනාවක්. SIM card එකක් නෙවෙයි. හරි. Then this is the transmission line. This is transmission line. This is microstrip. Okay. So if you consider this picture again, okay, this picture again, this plus is just like this one. This is strip. This is a copper strip. Okay. So copper are painted here. Copper gala තියෙන්නේ මෙතන. මේකෙත් තියෙන අර වගේම structure එකක්. We have a copper layer here. Then we have a substrate. Okay. We have a substrate here, that is a non-conducting material. Then again we have copper here. Okay. So these are called substrate actually. Okay. So there are different substrate we use to construct a microstrip. Yeah. Actually that is a square antenna. Okay. There are many type of antenna we use. This is a square antenna. Okay. And also rectangular antenna we use sometimes, the circular antenna we use. Okay. So there are different type of antenna we use for different application. Okay. So this is a basic antenna type actually. This is square. One is actually this is not, yeah, it is square, I hope. Yeah, it is a square one. Okay. This is a basic type of antenna. Okay. So if we need to do, for example, if you need to direct the radiation in some direction, or maybe if you want to have a wide direction, okay, that is we called half beam width. Okay, wide half beam width. Maybe you have to change this structure. Okay, change this shape. Okay, then you can have different radiation pattern. Okay. So that is related with the antenna design. Okay. So what I want to tell you is that I want to show you this transmission line. This is a transmission line, microstrip transmission line. Okay. So if you consider this one, this plus part is this one. This is small. You can see that this small strip is there, and minus is this ground plane. Okay. So this kind of any transmission line can be modeled like this. Okay. As a lump element circuits. Okay. So you can see that we have some resistor, inductor, then parallel resistance and parallel capacitance. Okay. So these are very much identical to what is called coaxial structure. Maybe you have learned this in electromagnetic subject. Okay, electromagnetism. Okay. Anyway, we are not much going to focus in on this lumped element equal circuits. Okay. So anyway, we can get this kind of circuits This is circuit model, lump element circuit model, equivalent circuit of the transmission line. Okay. Then we can use, maybe you can apply Kirchhoff law to this one. Okay. Then you can get some equation. Okay. So these are differential equation. Okay. So these are the differential equation in time domain. Okay. So these are known as telegraph equation. Okay. We don't need these things. Okay. Don't worry. Okay. You no need to remember these things because question not will come in this area. Okay. But you can see these things. Okay. Then it converted to phasor domain. So there is no time variable. Okay. Okay. So we have this kind of phasor domain through differential equation. Okay. Okay. So this differential equation, okay, again, we can have this differential equation, okay. So we have to solve this differential equation. Then we can find the value for this Vz and Iz, okay. So last time we started our discussion from here, maybe you can read, okay. So this is the total voltage at any point, at the general point, okay. So normally you place, we assume that we place this transmission line in Z axis, okay. Okay. So this Vz means this Z can be any location, no? Any voltage, any location voltage, okay. And Iz also the current, any the general current value, general current in a general point, okay. Then you can solve this equation, okay. And then you can get this equation, okay. This type of equation. This gamma is called the transmission constant, okay. This gamma is called, so this gamma is considered as transmission constant, okay. And the transmission constant is equal to this one, okay. This gamma is also can be written as alpha plus j beta. This beta is the phase constant, okay. For a lossless line, that means no loss there, okay. When the signal is going through a transmission line, we assume that there are no loss, okay. The transmission line has no loss, uh, power loss when it is propagating. The signal, I told you that if it is a transmission line, signal is propagating. Our signal is propagating. We will come to this point, okay. We will come to this point, okay. Uh, the no power loss means actually no attenuation, okay. There is no attenuation, okay. If the power loss is there, the attenuation is happen, no? Okay. So you can consider that there is no attenuation anyway. We will see when we are writing the equation, we will see it, okay. We will try to understand, okay. So for a lossless line, this alpha can be considered as 0, okay. So gamma is directly is equal to j beta. Actually, we write that equation, okay. Okay, and also we learned that the beta phase constant is equal to 2 phi divided by lambda. Lambda is the wavelength of the signal. 2 phi divided by lambda. Okay. Uh, so you can see that for a lossless line, alpha is equal to 0. Okay. Then our general voltage and current value will be like this. Okay. Uh, Previous time I told you this is plus, no? This is plus. Is the mistake there? Okay. Okay, I will explain this again. Okay. So if you consider any transmission line, if you consider any transmission line like this, okay, okay, this is a transmission line. It can be a coaxial, it can be a microstrip, anything, okay. And if you consider, let's say that Z axis is like this. Let's say that this point is Z is equal to 0, okay, and this transmission line is there, okay. Transmission line is there, okay. So if you consider any general point, okay, general point, okay. So we have learned that, okay, uh, in a transmission line, so we are giving a voltage, no, okay. So normally as an input, we are giving a signal, voltage signal, okay. So that voltage signal will generate a current signal. We have learned this, okay. But in a transmission line, it is propagating, okay. So you know that a signal is a function related with time only, voltage with respect to time, okay. But here it is propagating. So when once is propagating, voltage will be changed with time as well as the distance, okay. So this is a wave, this is a wave, and this is a signal, okay. So once you feed the signal to a transmission line, that signal is starting to propagate. That means it will become in a, it will be become a- it will become a wave, okay. So if you consider general point voltage wave Vz, okay, so that is equal to, okay, so if a signal is propagating, the signal is uh, going forward, that is we uh, denoted as V plus, as well as signal can be reflected, that is we uh, denote as V minus, okay. So this total Vz is equal to, if you consider any point, this total Vz will be, this total Vz will be um, forward plus reverse voltage, reverse voltage. Actually, these are not voltage difference, okay? These are not voltage difference. These are just voltage. These are just voltage, okay? That is what I take mistake, okay? Previous time yes, but these are not vectors, no. These voltages are not vectors, no. Voltage is a potential, no. It is a potential. ඒක විභවයක් නේ. So there is no direction for a potential, no. ඒක ශක්තියක්. It is just energy. For energy, there is no direction. Only magnitude is there. Only a value is there, but no, but no direction, no. Potential එක direction එකක් නැහැ නේ. විභවයකට direction එකක් නැහැ. Okay. But if you consider voltage difference or potential difference, it has a direction. For example, if here we have a high potential and here we have a low potential, so we have a potential difference in this direction. Okay. So that potential difference has a direction as well as a magnitude. So it is a vector. But if you consider potential, it is not a vector. I think I correct, okay? I'm correct, okay? So if we have a doubt, we will check with Dr. Udesh also, okay? I think that is correct, no? potential is just the energy, no? So it doesn't have a direction. It is just have a value, amount, okay? So we have to add them. But if you consider current, okay, the current is also, there is a forward current that is referred as plus and backward current that is referred as minus. Okay. So it has current. So that current, total current should be the algebraic sum, no? Because current is a vector. It has a direction. So I think it should be minus here. I think that is why we have put it minus, okay? Here we have to write minus, okay? Okay. So if you consider, okay, so it should be minus, okay? Here in book also it is minus, no, okay? But last time I think I told it plus, no? As I can remember, I told this as plus, okay? But it should be minus, okay? So this equation is very important. I will remind what is this equation again, okay? So, so if you consider this point, this is Z is equal to 0, okay? Okay. So let's say that the forward voltage at Z is equal to 0. That means V 0 plus, we can denote as V naught plus, okay? This is Z is 0, okay? Z is 0. Sorry, here this is Z, this is Z. Okay. So when the Z is 0, V naught plus, okay? Normally you put 0 here, V naught plus, and there is a backward also, okay? This is V naught plus, the backward one is V naught minus, okay? So there is a backward voltage at Z is equal to 0, that is identical to normally denoted as V naught minus. Okay. So if you consider the total voltage at Z is equal to 0, okay? So you can use this equation V0 Z is equal to 0. Total voltage, total wave, voltage wave is equal to V naught plus V naught minus. In the same manner, total current wave I0 is denoted that can be denoted, can be written as I naught plus minus I naught minus. Okay. So if you consider a voltage, this forward voltage in Z direction, okay, in Z direction, in this direction, okay, some point, okay, if this is V naught, if Z is equal to 0, if it is V naught plus, the forward here at Z, that means when Z plus this point forward voltage, I just put it as Z plus, okay? So that is equal to V naught plus e to the power, okay? E to the power this direction, okay? So let's say that here, from here to this point, the distance is Z. From here to this point, distance is Z. So it will be to the power J beta Z. It should be minus, okay? And the reflected voltage is equal to V naught minus e to the power plus J beta Z. Okay, you can write this like this. Okay, as well as current also you can write I plus Z as I naught plus e to the power minus J beta Z. Z is the length, distance. Okay, I naught Z is equal to I naught minus e to the power minus J sorry, plus J beta is. You can write like this, okay? So total voltage at Z point is equal to V naught Z. You have to consider this one VZ plus VZ minus. That means V naught plus e to the power minus J beta Z plus V naught minus e to the power plus J beta Z. The current also you can write, total current wave also you can write I plus Z, I minus Z. I plus Z is equal to I naught this one. I plus Z is equal to this one. For a general point, okay? I naught plus e to the power minus J beta Z plus I naught minus e to the power plus J beta Z. Sorry, this should be minus. Okay. So these equations are very important. Okay, try to remember this one. Okay. Z is the distance, yes. Z is the distance. This Z is the distance from Z equal to 0. මේ Z බිඳුව තැන ඉඳන් ඔය අපි සලකන we consider general point අන්න general point එකට තියෙන දුර common length එක. Okay, so that is Z. Okay. So these equations are there. We have last time we have learned these two equations. No? Okay, in previous time we have learned these two equations. Maybe you have understand it well. Okay, so if it is not still understand, you can just try to read this and try to understand. If you can't understand, you can ask me, then I can try to help you. Then when we are when we are doing some example, I think you will get this, okay? If there is a problem at this point, okay? When we are doing some example, you will get this, okay? Anyway, it is better if you can remember these two equations, okay? And there is another things we have also learned, okay? So if you if you consider any point is a point, there is a forward voltage Vz, okay? That is V equal to this one. There is a reverse voltage that is V equal to this one, okay? And there is a forward current that is represented as I plus Z, this one. There is a reverse current, I minus Z. So it is also this one. And if you know that V equal IR, okay? So if we divided V divided by I, you will have a resistance, okay? You will have a resistance or impedance. This is also referred as impedance, okay? Now, if you divided this plus voltage, plus the forward voltage with forward current, what will be the value? It will be V naught plus e to the power minus J beta Z divided by V naught minus e to the power J beta Z. So minus, sorry, I'm not okay. I'm sorry. Okay. Sorry. Thank you. Okay. So this one should be I naught. I naught plus e to the power minus J beta Z. You can see that this one and this one divided, and you will have E naught plus I naught plus. Okay. And this is equal to impedance. We called it Z naught, and we define it as characteristic impedance. Okay. Now tell me, and also the characteristic impedance can be written using this backward current and voltage. So it will be V naught minus divided by I naught minus, and it should be minus value. Okay, here we will have a minus value. So you have to divide in by minus. You have to multiply this by minus. Okay. So this is a naught is equal to this unknown, this V naught plus I naught plus. Okay. So this is we call characteristic impedance. Okay. Now I ask you one question, not a small question. If you consider a transmission line like this, okay, if you consider a transmission line like this, okay, let's say that this is Z is equal to 0, okay, and forward voltage is V naught, backward voltage is V minus, forward current is I naught plus, backward current is I naught minus, okay. Uh, okay, so we have a transmission line like this, okay. So if you consider 2 points, for example, this is the same transmission line. If you consider this point, let's say that it is mm, plus L1 distance from this Z is equal to 0. And if you consider another location, it is in this direction. So if you consider Z is in this direction, this will be a minus direction, no, minus Z value. So let's say that it is minus L2 or something. Okay? And what you think about two characteristic impedance? Here, let's say that in this point Z naught 1 and this point Z naught 2. What can you say about these two impedance, characteristic impedance? Are they same or different? Can you tell? Are these two same? Yes, very good. Okay, those are same actually. Okay, because if we write the equation, okay, so if we write the we set the equation, we set, sorry, we plus Z here, okay, it will be forward one, okay. So in this point, it will be V naught plus, okay, V naught plus. Now L1 is in this direction, Z direction. So it will be e to the power minus J beta L, okay, because it is plus L1, okay. And if you want to I plus Z, okay, I plus Z, so it will be I naught plus, again L1 is here, so it will be e to the power minus J beta L1. So this one cancel. You will have V naught plus I naught plus. Okay. And if you consider this point, again, if you consider V Z plus forward voltage, total voltage, forward voltage, not the total voltage. Okay. So it will be, in this point, it is V naught plus. And now you can see that now the L in minus direction. So it will be e to the power minus J beta minus L2. So it will be plus. Okay. And if you consider IZ, again, IZ will be, here the forward current is I naught plus e to the power minus J beta. Again, this L2 is minus value, this direction. So minus L2. Okay. So again, you can see that this part cancel. And here also you will have the value V naught plus I naught plus. This is Z naught 1 and this is Z naught 2. So what you can say? Z naught 1 is equal to Z naught 2, no? Definitely. Okay. So you can see that the characteristic impedance is not changing along the transmission line. Okay. not dependent on this. Yeah, yeah. Not dependent on the direction also. Direction and location not depend. Okay. If we simply say through a transmission line, the characteristic impedance is not be changed. This will not be changed. This is a constant. Okay, this is a constant. So this is very important. Okay, okay. Now, I will ask you another question. Okay, just try to do it. Mm, Let's say that we have a transmission line here. We have a transmission line like this. Okay, this is a transmission line. Now I will write it like this. This is a transmission line. Okay, and this is the line side. This is the ground. Okay, and we have a load here. We have a load here like this. Okay, so this is a load. Okay, now you can see that this is a transmission line. That load is connected to the ground. Okay, so actually, if you consider it is somewhat like this. Okay, if we consider transmission line, for example, maybe a copper strip or something. This is the transmission line. Right? We have connect a impedance ZL. This impedance can be resistive, capacitive, or inductive. Anything. Okay. And if you ground this like this. Okay. So both are same. Okay. Let's say that this point is equal to 0. That means this point is equal to 0. Okay. And this is the Z direction. This is a direction. Now, can you write the equation for ZL? Can you write the equation for ZL? Okay, because you know that in Z is equal to 0. Okay, Z is equal to 0. There is a total voltage VZ 0. Sorry, V0, and there is a total current IC. So you can write what is V0, V0 plus V0 minus, I0 is I0 plus um, I0 plus minus I0 minus. Okay. So anyway, we have V0 and I0. Okay. This is the voltage. This is the voltage here. Voltage and current. Okay. So this current is going through this ZL. And voltage is also between this ZL and transmission line like this. Okay. This is the V0 and this is the I0. Okay. So if we apply Kirchhoff law, ZL is equal to V0 divided by I0. Correct? Yes. We equalize it. Okay. But if it is um, impedance, that means it can be a capacitive impedance or reactive impedance. Okay. Then the phase is not same in V and I. The phase will be different. Okay. So we don't care about the phase. Okay. We just see the quantity. Okay. So ZL is equal to V0 I0. Okay. So what is V0? What is V0? That is the total voltage at Z is equal to 0. So in our usual notation, V0 plus is the forward voltage, V0 minus is the backward voltage. And I0 plus is the forward current, I naught minus is the backward current. Okay. So what is V naught? V naught is nothing but V naught plus V naught minus divided by what is I naught? I naught is I naught plus I naught minus. Is this correct? Is this correct or wrong? මේක වැරදිද හරිද? මම එළියට. Yes, very good. This should be minus. Okay, this should be minus. This should be minus I naught. Okay. Then we will try to get rid of this I naught. Okay. So we know that V naught plus divided by I naught plus is equal to Z naught. No? So I naught plus is equal to V naught divided by Z naught. Okay. V naught divided by Z naught. So you can write this as V naught plus V naught minus divided by V naught plus divided by Z naught minus V naught minus divided by Z naught. Okay. So you can see that you can get the common denominator, then it will be V naught plus minus V naught minus. Then you can get this Z naught here. Okay. So you can write like this. ZL is equal to V naught plus V naught minus divided by V naught plus minus V naught minus. Z naught. V naught plus V naught minus V naught plus minus V naught minus. Okay, so you can write this. Okay, then you can see that if you take this one, okay, ZL V naught plus minus ZL V naught minus is equal to V naught plus Z naught plus V naught minus Z naught. Okay, so now I want to get V naught and V naught plus and V naught minus one side. Okay, so here is at L V naught plus, and I will take this one. So it will be minus V naught plus Z naught is equal to, I will put this here. So it will be ZL V naught minus ZL V naught minus yes. Here we have plus Z naught V naught minus. No, okay. Now you can get this V naught minus minus. V naught minus as ZL plus Z naught, and V naught plus you can write as ZL minus Z naught. Okay. So V naught minus divided by V naught plus you can write as V naught minus divided by V naught plus you can write as ZL minus Z naught divided by ZL plus Z naught, like this. Okay. So what is this V naught? This is the reflected wave. This is the reflected wave. This is the forward. This is the forward. Okay. So reflected wave means forward wave means the wave is trying to go through this in this direction. Take one of both sides. I didn't get it. Take one. What it mean? I can't understand. Ah, yes, yes. Equation, yeah, you can get the equation up and okay. Is this wrong? Like, where is it? It is correct, no? Okay. Okay, you can get upside down also, okay? So here you can see that this is a reflected wave. Reflected wave, sorry, forward wave, V naught plus. Forward wave means now the wave is trying to go through the impedance, isn't it? Reflected means when you are sending a signal, it is reflecting, part of it reflecting. So that is V naught minus. Okay. Now you can see that when if you have this kind of one, is a transmission line, and if you connected it to a impedance, okay. So one a wave is forwarding V naught plus. There is another part that is reflecting. So that is V naught minus. Okay. So is this okay or not? Is this okay or not? This reflection is okay or not? Is it good or bad? Normally V naught plus is plus high. Okay. V naught plus is high because it is a forward. V naught minus is the reflected. අපි යවන signal එක තමයි V naught. Reflect වෙන එක තමයි V naught minus. Okay. So always sending signal is greater than the reverse signal. Okay. දැන් මේක V naught plus කියන්නේ මේ මෙතන resistor එක හරහා මේ ZL හරහා යවන එක. V naught minus කියන්නේ මේ ZL ආපහු reflect කරලා යන එක. Okay. Yes, very good. Then it is bad, no? Why? For example, let's say that you have an amplifier here. You have amplifier here, you amplify your signal. Then you need to send it to another level. Let's say that filter. What happened? So you are sending a signal here, wave here. So this filter will again reflect some wave. Okay. So not total signal is going inside the filter, no? If forward is V naught plus, the reverse is V naught minus, this is the voltage value or signal getting into the signal filter level. Okay. So it is a loss, no? It is a signal loss. So it is a reflection loss. We called it reflection loss. Sometimes we called it it's called reflection loss. So Yeah, normally it happen like this, okay? So we have a signal like this, okay? Now reflecting. Reflecting means reflecting like this, okay? Then actually it is just like destructive, okay? But it is not destruct, this, it is not disappear, it is making a standing. It is making a standing. Now the wave is not propagating. Wave is standing. Wave is static. Wave is not, wave is not moving. It is stationary. This is we call standing wave. We have learned this, okay? ස්ථාවර. These are called ස්ථාවර තරංග. අර සරසුලකට එහෙම පින්බහම වෙන්නේ. මෙහෙම යනවා මේ සිග්නල් එක මොකක් හරි වායු සිග්නල් එක මොකක් හරි ශබ්ද සිග්නල් එක ඊට පස්සේ මෙතනින් යන්න නැති හින්දා ඒක ආපහු රිෆ්ලෙක්ට් වෙනවා අපේ පැත්තට. එතකොට මෙතන හදන්නේ standing wave range. Standing wave. හරි. Okay. So it generate a standing wave. Okay. So if we have a reflected voltage, there is a standing wave. Okay, so that is not a good thing. Okay, because reflected wave is there. Reflected wave is there. Okay. So what we should do if we need to reduce this? If we need to reduce this, what we have to do? අපිට මේක අඩු කරන්න ඕන නම් මොකද්ද කරන්න ඕන? What we have to do? Let's say that you want to zero this. No, not V naught plus. Okay. If you are increasing V naught plus, what happened? Again, V naught minus is also increasing. Forward power එක මේවා කරනකොට ආපහු reflect වෙන ප්‍රමාණයක් වැඩි වෙනවා. හරි. එතකොට ඒක හොඳ එකක් නෙවෙයි. ඊට වඩා හොඳ දෙයක් තියෙනවා. දැන් හිතන්න මෙයා බින්දුව, ඒ කියන්නේ reflection එක 0ම කරගන්න ඕනේ කියලා. What you have to do? V naught minus V naught plus. මෙයා 0 වුණොත් මේක 0 වෙනවා. If you want to make this guy 0, the total will be 0, no? So it is equal to this one. To make this 0, what you have to do? මෙයාව 0 කරන්න. To make this 0, what you have to do? මෙයාව 0 කරන්න මොකද කරන්න ඕන? No. මෙයාව ඉන්ෆිනිටි කරනවට වඩා ලේසි එකක් නැද්ද කරන්න? Want we have easy things. You are correct, okay? Mathematically, if you increase, if you make this infinity, it will be 0. And if you make this 0, what happens? Again, it will be 0. Yes. What we have to do? We have to equal this ZL to Z naught. Yeah, I could understand. Yeah, I could understand. Okay. So your answer is correct. Okay. මට තේරෙනවා සමාන ගහ දැන් මේකට කියලා. හරි. What you have to do is you have to make equal this ZL Z naught. This is we call matching. Okay. This is we call matching. We will learn this later. Okay. This is very important thing. Okay. But we are not going to learn this time. Okay. We will learn this later. This is called matching. They're very important things. Okay. So to reduce this reflection, we have to make this impedance equal. Okay. Load impedance and characteristic impedance equal. Okay. So that is we call as matching. And this is this one. This is a reflection. We have a forward value. We have a backward value. This is we call as reflection coefficients, gamma. This V naught minus divided by V naught plus. This is referred, sorry, tau, okay? We are using tau. Tau. Okay, so this is reflection coefficients. Reflection coefficients. Okay. So that is very important. Okay. Mhm. Okay. Now I will give you one things to do. Okay. Uh, දැන් පන්දුමාල් අපි දැන් මෙතනදී මේ තියරිටිකල් දේවල් කතා කරන්නේ ඒවට තව ටිකකින් තව කියන්නේ අපි දැන් ඉස්සරහට යනකොට අපි අර ෆිල්ටර් ඩිසයින් ඇම්ප්ලිෆයර් ඩිසයින් වලට එනකොට තනිකර තියරිටිකලි පැත්තෙන් මිදිලා ඉම්ප්ලිමන්ටේෂන් පැත්තට තමයි යන්නේ හරි සිලේට ඩිසයින් ඒ ටික කරනකොට ඒක ටිකක් අමාරුයි හැබැයි තියරිටිකලි පාර්ට්ස් ඕන වෙනවා නැතුව කරන්න බෑ හරි ඒක අපි බලමු කොහොමද කරන්නේ කියලා okay now I will give you one work so try to do this. So let's say that you have a transmission line like this. Okay, and this is Z is equal to 0. Okay. So do this as a homework. Okay, do this as a homework. Uh, so today we will stop from here. Okay, don't worry, we have enough time to do cover the LOs. Okay, so we will stop here. But so anyway, try to do this homework before next week. And also, if you can just try to talk with others, maybe they are not selecting the subject. Okay. So anyway, if they have a participation issue in this time, I think we have to change the time. Okay. ඔක්කොටම එන්න බැයි නම් මේක චේන්ජ් කරන්න වෙනවා මම හිතුවා ඔක්කොටම එන්න පුළුවන් ඉතින් ටයිම් එකේ ප්‍රශ්නයක් හින්දා කට්ටිය ඇවිල්ලාද නැද්ද කියලා චුට්ටක් ඔයා පොඩ්ඩක් පුළුවන් නම් හොයලා බලන්න මම පොඩ්ඩක් වන්ටත් අහලා බලන්න. Yes. Okay, thank you for reminder. Okay. Uh, yes, I will take that in. Okay, I will give you this question. Okay, so let's say that this is some kind of impedance ZL, and this is Z is equal to 0. Okay, this point Z is equal to 0. Okay, and this point let's say that this is this point. This is the Z direction. Okay, this is Z direction. Let's say that this is L. That means it is minus L. Okay, this is minus L direction. Okay, this is a transmission line. Okay, let's say that characteristic impedance of this transmission line is Z mod. Okay, so try to find a value for this impedance Z. Let's say that it is ZE. Okay, so try to find a value using Z naught and L. Okay, and also ZL will be there. Expression for ZE. So if I write Z in is equal to here, the wall here in this point, okay? So so you know that Z in is equal to VZ total VZ divided by total IZ. Okay, this is total. Okay, so we know that VZ is equal to V naught if the voltage here, let's say that V naught plus, as usual notation, V naught minus, the currents are I naught plus, forward current is I naught plus, backward current is I naught minus. So you can write this as V naught e to the power minus j beta L. L is in this direction, so it will be minus A. is plus V naught minus e to the power plus j beta minus a. Okay. Same way you can write the current as I naught plus e to the power minus j beta minus L minus V naught, sorry, I naught minus e to the power plus j beta minus A. Okay. So you can write like this. Okay. Then what you have to do, uh, maybe you can, so you need to get rid of these terms. Okay. V naught minus I naught and I naught minus. Okay. So I think you can get rid of it using this equation. This one you can get rid of and you can put ZL and Z naught only in this equation. Okay. Try to make it. Okay. So finally you will be able to get the equation for Z in that is equal to Z naught. Okay. Z naught um, Z naught into ZL. I can't remember the equation. Okay. Here we have, and here also, here they get this equation. Okay. Get those equation using Kirchhoff law. Okay. Using the field analysis also, we can get the same equation. Okay. 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 So this so you can see that telegraph equation also can be derived using so we have seen this one. This is the time domain signal. Okay. So it can be derived using uh, field analysis also. Don't worry. Okay. We are not going to study them. Okay. So anyway, finally you can get this equation to equation. Okay. Um, and this is the equation again we have derived. Okay. So you can check it. Then so you can see that Z in, you can get this equation. Okay. Z in. For Z in, you can get that term. Okay. Z in means the impedance here in this point is at okay. So you can get this equation. Okay. So try to get this equation. Okay. So you can make this, you can try to don't waste too much time to this one. Okay. Because this derivation is not much important. Okay. ඒක mathematical වැඩක් නේ එතන තියෙන්නේ. මේක මෙහෙන් ආදේශ කරලා හරි. ඔය කට්ටියට ඔයාලට ගන්න පුළුවන් මෙන්න මේ equation එක. මෙන්න මේක තමයි වැදගත්. හරි. මෙන්න මේක තමයි වැදගත් එක. හරි. So what it means? What's the theta? Yeah. This one. This one is the reflection coefficients. V naught minus divided by V naught plus. No. It is the reflection coefficients. Okay. I think we have defined. I will upload this recorded lecture. Okay. Then you can go through it and get the idea again. Okay. So anyway, try to get this equation if possible. No need. Okay. Actually, this is very important. This is we call transmission line impedance equation. This is we call transmission line impedance equation. You can using this basic equation, you can get this. So what that means? That means if you have terminated a transmission line, this is a transmission line. If you have terminated a transmission line with the ZL load, okay. If transmission line is terminated by a ZL, okay, ZL, input impedance of the transmission line, okay, okay, input is impedance, that is the input impedance of the transmission line, is given by that equation, okay. So if you consider L length from this point, okay, L length, the impedance here, impedance in this point, it is not a characteristic impedance, okay. Characteristic impedance is same below, okay. This is the total impedance, VZ divided by IZ, okay. Don't get confused, okay. Don't get confused it with Z0, okay. Z in total impedance at the edge of the transmission line is equal to Z0 characteristic impedance into ZL plus Z0 tan beta L. Beta is the what is called beta is the phase constant. Okay, so this one beta is there. You know that beta is equal to 2 pi lambda. Okay, beta is equal to 2 pi lambda. Tan beta L divided by Z0 plus ZL tan beta L. Okay, so this is very important equation. We call this transmission line impedance equation. Okay, transmission line impedance equation. So next week we need to do some derivation using this one. So this transmission line impedance equation. Okay. So before that, try to understand this very well. Yes, 2 phi lambda is equal to beta phase constant. Okay. Lambda is the wavelength of the frequency. V equal F lambda. Okay. So if you are using, so this beta is depending on the frequency you are selecting. Okay. Because beta is equal to 2 pi divided by lambda. Beta is related with the frequency. It is called as phase constant. So this is transmission line impedance equation. So that is very important. Okay. Uh, so we will stop here now. So we have learned this one actually finally. Okay. Yeah, sorry. I will take that example. Okay. And next week we have to do some derivation using this transmission line equation also. Maybe you can try to get, okay, no, we will do it, okay, otherwise it will be a burden for you, okay. So anyway, I will review the attendance, okay.